Bismillahirrahmanirrahim. Dear students, I'll start lecture number 2 of week number 14, and in the initial part of this lecture I'll discuss uh, jointly Gaussian random variables. So first topic in today's lecture is jointly Gaussian random variables. As a special case, we'll discuss a distribution of two Gaussian random variables. So effectively, this is a jointly Gaussian bivariate distribution, and for a jointly Gaussian bivariate distribution, or in other words, bivariate Gaussian PDF. What is the expression? Let me write the expression that is simple. Please do not get confused with the apparent complexity of the expression. So we say that x and y are random variables. X and y have a bivariate Gaussian PDF if the giant PDF of x and y is something like this. I'll have to use the next page because the expression is a little longer. The bivariate Gaussian distribution or jointly Gaussian distribution of two random variables x and y, where x and y both are Gaussian random variables. The expression can be written as such: f sub x comma y of x comma y, and that is equal to exponential negative exponential of x minus mu 1 over sigma 1 whole square plus y minus mu 2 over sigma 2 whole square minus 2 rho x minus mu 1 times y minus mu 2, and this is divided by sigma 1 sigma 2, and this all is divided by 2 times 1 minus rho square, and this all exponential is scaled with 1 over 2 pi sigma 1 sigma 2 under the root 1 minus rho square. As I said, do not get confused with the complexity, the apparent complexity of this expression. This is simple to comprehend. I'll show you how. But first, the parameters. The parameters are mu 1 and mu 2, which are real numbers, and these are also the mean values of random variable x and random variable y. So mu 1, I have not intentionally written it as mu sub x and mu sub y, because then it would have made the expression even more complicated. So mu 1 is basically the mean of random variable x, and mu 2 is the mean of random variable y, and these two are real numbers. The other parameters are sigma 1, which has to be greater than 0, and then sigma 2, it also has to be greater than 0, and these are obviously the standard deviations of random variable x and random variable y, and then rho, which is greater than or equal to -1 and less than or equal to 1, which is the correlation coefficient. So now this is a complete giantly Gaussian bivariate distribution. This is how we write it, and now I'll show you the expression, the shape of this distribution. So this is just imagine that if you have a random variable x which is Gaussian, so it will have a bell-shaped curve. We have another random variable y on the other axis. This variable y also has a Gaussian shape, a bell-shaped curve. So both put together shall give you something like this. So it's now a proper bell whose edges are extending towards infinity, and you can simply see that if we slice this bell with a plane parallel to xy plane, then we get a circle on the edge where we had sliced this bell, and this circle will be obtained when the variance of x and variance of y, or in other words standard deviation of x and standard deviation of y, are equal. If the standard deviation of one of these random variables is greater or smaller than the other random variable, then you will have a squeezed bell from one axis, and in that case if you slice the bell on the edge of the slice, you will get an ellipse, either extended more towards semi-major axis on one of the variables. So please do keep in mind that when you have a bivariate Gaussian distribution of something like this, this is the generic expression. Your plot will be a Gaussian distribution, a bell of a shape similar to this. So now I'll do a small observation, and I'll derive an important conclusion from here. So now observe that if we have rho is equal to 0, rho is the correlation coefficient, sigma 1 and sigma 2 are basically the standard deviations of random variable x and random variable y respectively, and mu 1 and mu 2 are the means of random variable x and random variable y respectively. So now I say that if the correlation coefficient is put to 0, which also means that x and y are uncorrelated. So now if I say that x and y are uncorrelated, which means rho is equal to 0. If that is the case, what will be the shape of this distribution, and what conclusion can we draw from this condition? So now imagine that we put rho is equal to 0 here. So this will be basically under root of 1. This will be the denominator here will be simply 2. So the expression now becomes negative exponential of x minus mu 1 over sigma 1 whole square. Pardon me, this was minus minus y minus mu2 over sigma 2 whole square, and then this part goes to 0. Sorry, if you put minus here, then it has to be plus. When you expand it, then this will make it negative exponential. So now putting rho is equal to 0, we get f sub x comma y of x comma y equal to exponential of minus x minus mu1 whole square over 2 sigma 1 square and minus y minus mu2 whole square over 2 sigma 2 square all divided by 2 pi sigma 1 sigma 2. So what we have done is we have distributed this negative sign on both of these. This is already 0. This is basically all becomes 2 because this is 2 times 1 minus 0, and this term also becomes 1. So effectively this expression turns into this expression. You should work this out at home. So now I can write it as something like this: exponential minus x minus mu1 whole square over 2 sigma 1 square times exponential minus y minus mu2 whole square over 2 sigma 2 square, and this can be broken into 2 pi under root times sigma 1 into 2 pi under root times sigma 2. So now you can very easily see a clear separation between the two at this particular point. So we can very easily see that this expression is nothing but a PDF of a Gaussian random variable x. If you recall, the PDF of a Gaussian random variable was e raised to power minus x minus mu over 2 sigma square divided by all this. So now this is the expression for one-dimensional Gaussian distribution x times this is the expression for one-dimensional Gaussian distribution y. And so we have been able to write this giant distribution of x and y Gaussian distributions, the giant bivariate distribution. We have been able to write it as a product of the individual distributions. So this is nothing but the condition for independence of two random variables x and y. And so we can now conclude, since we have been able to write the giant distribution of x and y, giantly Gaussian bivariate distribution of x and y, by putting rho is equal to 0, or in other words we say that x and y, if x and y are uncorrelated, the general expression turns out to be this, and which ultimately leads us to this particular product, which is nothing but a condition for independence. So hence we can say that any uncorrelated Gaussian random variables are also independent. So this is now our conclusion. Please keep this in mind. Now, if the giant bivariate Gaussian distribution, if one of the variances is greater than the other random variable, then obviously we'll have a squeezed bell on one of the axes. The bell will be squeezed along the axis whose variance is smaller than the other axis. But what about the conditional Gaussian bivariate Gaussian distribution? So this is what we obtain if we put some condition. So if we have expression something like this, f sub y given f, x of y given x, you condition one variable on the other, both are Gaussian. So the giant Gaussian distribution will be sliced, and each of these will be Gaussian along one axis. The other part is basically sliced out. So please do visit such expressions and plots, and do search about these in your textbook, and you will find some interesting plots. This was a quick initial look at giantly Gaussian bivariate distributions. Let me quickly give you now what we mean by more than two random variables, more than two continuous random variables. When we put them together, how can we write it? This topic is basically similar to the one that we discussed in case of more than two discrete random variables. Remember, there we had multiple summations and PMFs and CDF. Here we'll have multiple integrals and PDFs and CDFs. So the topic, a quick topic, next topic is more than two continuous random variables. So here obviously we'll have multivariate joint CDF first. As I told you many times, you utilize the CDF expression first, and from there you can differentiate and find the individual or marginal PDF. So the giant multivariate CDF. This is simple. We write it as f sub x1, x2, so on till xn of x1, x2, so on till xn. And this is nothing but the probability that x1 is less than or equal to this number, x2 is less than or equal to this number, and so on, xn is less than or equal to this number. So the definition is the same. How to find the giant PDF then? Giant multivariate PDF from this CDF. You know that the PDF is nothing but the derivative of the CDF. So if we want to have the giant multivariate PDF f sub x1, x2 till xn of x1, x2 till xn, this will now be a partial derivative, nth partial derivative or n partial derivatives of this CDF. So we'll write it as curly n of the CDF x1 till xn of x1 till xn over curly x1 till curly xn. So you see the concept of two random variable, giant random variable, is simply extended to more than two random variables. What about finding the marginal distributions? Marginal distributions to be obtained from the giant continuous distributions. So this is again very simple. You simply integrate the giant distribution on all those variables uh, which are missing in the desired marginal distribution, and this is what we exactly did in the case of multiple discrete random variables and marginal distributions over there. For the case of discrete random variables, the same concept is extended, applicable for the case of continuous random variables. So I'll write it in the form of a quick theorem. Suppose you have a PDF of four random variables w, x, y, and z of w, x, y, and z, and you want to find the marginal distribution of x, y, and z, marginal PDF. So now your giant distribution is of the four random variables, and you want a marginal distribution on three random variables. So you will integrate the giant distribution on the variable which is missing here. The variable missing here is w. So you will integrate with respect to w. You will integrate on w. But if you want to find a marginal distribution of say two random variables w and z, then you will have to integrate the giant distribution or the giant PDF f sub w, x, y, and z, w, x, y, and z on two variables which are not here but here. So except w and z, we have x and y. So you will have dx and dy. And suppose you want to find f sub x of x from the giant four-dimensional distribution of w, x, y, and z. So now you will have three integrals and the giant distribution wx, y, z of w, x, y, and z, and you will integrate it on w, dy, and dz. So this is simple. The concept is the same as was the case in discrete multiple random variable. You simply extend that concept. I'll give you one quick note on the independence of n random variables in the next part of the lecture. So if we have n independent random variables, the giant PDF, say x1, x2 till xn of x1, x2 till xn can be written as the product of the individual PDFs. So this should be f sub x1 of x1 times f sub x2 of x2 times so on f sub xn of xn. So if you know that n random variables and continuous random variables are independent, so then this expression is an automatic result. The remaining expressions for or the remaining formulas for example, the expectations can be simply extended and derived or can be imagined from the concept of discrete multiple random variables. So here I'll stop this part uh, of the lecture and I'll move on to an important topic of how to find probability models of derived random variables, or in other words, how we can uh, transform random variables from one random variable to another random variable. So please concentrate and do understand uh, this topic as well, which is about transforming random variables. Transforming continuous random variables. Sorry. This is an interesting topic. Transforming a continuous random variable would mean that suppose we have a random variable y which is a function of a random variable x, and we say that this is your source random variable and this is your target random variable. And how can you find or transform one random variable into another random variable? Which means you have y as some functional form applied on x, then what will be the distribution of x if you know the distribution of y, or how can you represent x in terms of y if you already know y in terms of x. So you know that the probability that the random variable x lies in the range x and x plus dx. The probability that the random variable x lies in this range is simply the probability that x is greater than or equal to x and less than or equal to x plus dx, and this is nothing but, as per the definition, the PDF of the random variable x. But since y is related to x in this fashion, so this probability must be equal to the probability that y lies between the random variable y also lies between small y and y plus dy. So let me first complete it, the expression, but this probability must equal the probability that the random variable y lies in the range y and y plus dy. This is important to understand. Y and x are related in this way. Y is obtained by applying a functional form on x. X is the source random variable, y is the target random variable. We know that the PDF of x is written by definition in this way, but since y and x are related, so this probability should be equal to the probability that y also lies in this small range. So if this is the case, we can simply write that f sub y of y dy, which means the change, the integral, not the change and integral, but this product f sub y dy is equal to plus f sub x of x dx if the function g is increasing. If g is a monotonically increasing function, and it is equal to minus f sub x of x dx if g is decreasing monotonically. It has to be monotonically increasing or decreasing in that small range dx and dy. So now we can collectively write this expression as f sub y of y dy absolute is equal to f sub x of x dx. And if that is the case, we can write that f sub y of y is nothing but f sub x of x dx over dy absolute. This is already positive because this is probability distribution. So we have now been able to somehow write the relation between the PDF of y, which is the target random variable, and the PDF of x, which is the source random variable, if we know the functional relation applied on x through which we obtain y. So by using these basic definitions, we have been able to write this expression. This is an important expression because this is how we transform a random variable x into random variable y, and obviously then random variable y can also be transformed into random variable x. So please keep this relation in mind. We'll use this relation to transform x into y. I'll do a few examples now. Important examples. Which will hopefully further clarify the concept. So my example 1, with respect to transforming the continuous random variables. So we are given that the PDF of x is e raised to power minus x square for x greater than or equal to 0, and we say that let y is obtained by applying a functional form on the source random variable x, and the functional form is x square. So we are asked to find the PDF of y. How can we approach this solution? This is simple. Remember, the PDF of y is basically the PDF of x times the absolute of dx over dy. So if everything is positive, so then you don't need to even put the absolute. So the PDF of y is equal to the PDF of x times dx over dy. So here we are required to find the PDF of y. We have PDF of x. What we need is dx over dy. So for that we have to first write x in terms of y. So now here we have x is equal to plus minus under root y from this expression. X square is equal to y, so x is equal to plus minus y under root And so this implies that dx over dy is equal to plus minus 1 over 2 under root y. And therefore we can write f sub y of y is equal to the PDF of x times dx over dy. We'll take the positive part only here, the positive part. So what is f sub x here? F sub x is, let me first write the formula. F sub x of x times dx over dy. And what is f sub x here? E raised to power minus x square. And what is dx over dy? Let me take the positive one. So it is 1 over 2 under root y times what is f sub x? E raised to power minus x square. But you see, this is not completely in the form of y. So we have to somehow replace this in terms of y. So this can be written as 1 over 2 under root y times e raised to power minus, and what is x square? It is simply y. So now our PDF of y is complete, obviously for y greater than or equal to 0. So you see how easily and quickly we have been able to transform one variable into another variable, or we have been able to find the PDF of the target random variable if we know the PDF of the source random variable and the functional form between the source and the target random variable. We have simply utilized this formula. I'll strengthen your understanding of the concept by doing at least one more example. It's a little more complicated but not difficult. So first, let me write the statement of the example. Assume a sinusoidal signal x, which is cos omega t, where the signal is x, which is varying in this form, cosinusoidal form, with respect to time, and this is the frequency. So where the signal has random frequency omega that varies uniformly in the range omega greater than or equal to omega 1 and less than or equal to omega 2. This frequency is represented by random variable capital omega, and we are asked to find the expectation of omega and expectation of the random signal x. So this is an interesting question. We have a sinusoidal signal x that is varying in a cosinusoidal form with respect to time, and the frequency is omega, that is a uniformly distributed random variable between omega 1 and omega 2. So this random variable is represented by capital omega. So now we are asked to find the expectation of capital omega and expectation of the random signal. or the random variable x in this question. Now, since omega is uniformly distributed, that is, we can write that f sub omega of omega is equal to 1 over omega 2 minus omega 1. You know how to write the PDF of a continuous uniform distribution. So if this is the case, then the expectation of omega is what? If you recall, the expectation of any continuous random variable, say n, is nothing but the integral n times f sub n of n dn, which means you multiply the variable with its distribution and then you integrate and you ultimately get the expectation of that random variable. So for the case of omega, you have from omega 1 to omega 2 the random variable omega times f sub omega of omega d omega. So this is nothing but now integral omega 1 to omega 2 1 over omega 2 minus omega 1, which is the PDF of omega, times omega times d omega. So now you simply do the integrations. So if you do the integrations, you will obtain something like this. You keep on doing the integration, you should ultimately reach as omega 2 plus omega 1 all divided by 2. Please do take this as a small homework. This should not be a difficult integration. You have to somehow reach from here till here. Remember the integral is from omega 1 to omega 2. And you see now this should be the obvious result, because conceptually if you have a continuous uniform random variable, then the expected value or the average should lie in the middle, and the middle between omega 1 and omega 2 can be obtained by adding them up and dividing by 2's, and so is the case here. So the expectation of omega is simply omega 1 plus omega 2 divided by 2. But this is the first part of the solution. We also need to find the expectation of x. Remember, this is a case of transformation of one random variable into another, because you see cosine is a functional form, t is time. The variables here are omega, which is continuous uniformly distributed, and x, which is basically obtained by applying the functional form of cosine on the random variable omega. So the relation is between two random variables, the random variable x and the random variable omega. The distribution and the range of omega is given in the statement of the question. So as yet we have been able to find the expectation of omega, but now we'll attempt to find the expectation of x. So x and omega are now related, as by definition f sub x of x is equal to f sub omega of omega d omega by dx. This should be simple to understand. If you recall, I had derived this relation of transformation between the two random variables. The target random variables distribution and the source random variables distribution are related in this way, and then you multiply it with dx over dy. So here you see now x is your target random variable, y because x because x is represented by applying a cosinusoidal functional form on omega. So omega is your source and x is your target. So if that is the case, the distribution of the target is basically the distribution of the source times d source by d target. D source by d target. So now this is obvious, and obviously x absolute is less than or equal to 1. Why? Because of this cosine, the amplitude of cosine is maximum plus 1, minimum minus 1. So x can not go beyond plus and minus 1. So we have written x absolute less than or equal to 1. So now we have to ultimately plug in d omega or dx. We already know f sub omega of omega, so if we can find this, we'll be able to find the distribution of x, and if we know the distribution of x, we can easily find the expectation of x, which is the second part of this question. So now you know that as x is equal to cos omega t, this implies omega is equal to 1 over t times cos inverse of x, and therefore we can write that d omega over dx is equal to 1 over t under the root 1 minus x square. So here are two small simple homeworks. This is so simple, just one small homework. Do perform this differentiation. At home. So we have obtained d omega by dx. We already have f sub omega of omega, so we can complete this equation. So our this equation now becomes f sub x of x is equal to f sub omega of omega, which is nothing but a uniform distribution between omega 1 and omega 2. So f sub omega of omega is nothing but 1 over omega 2 minus omega 1. So we write it as 1 over omega 2 minus omega 1 times d omega by dx, which is 1 over t times 1 minus x square under the root. Say this is my equation A. So we now have this equation. We can use this equation to find the expectation of x. You know that the expectation of any random variable x is basically integral in the applied limit x times f sub x of x dx. So the expectation of x here will be integral -1 to 1. Why? Because the range of x is from +1 to -1. X times f sub x of x dx. So now we can write it as okay, what is f sub x? 1 over omega 2 minus omega 1 times 1 over t times 1 minus x square under the root. So I can write it as 1 over omega 2 minus omega 1. And remember, this is for the random variable x. This is nothing but a constant, a scalar. So it can be taken out of the integral sign, and the rest is integral -1 to +1 x times the remaining part of f sub x, which is 1 over t times under the root 1 minus x square dx. And so when you perform this integral, you will have some interesting observation. You will ultimately have an interesting value of the expectation of a random variable x. What is that value? I'll keep that as your homework. Once you have attempted that, the other instructor, Mr. Zever, will also give you the answer. The answer should be obvious, but you have to perform this integration. Take this as homework. So now you see we have been able to transform, we have been able to attempt two nice interesting examples on how to transform one variable to another. The basic expression, basic relation, basic formula is this. The PDF of the target random variable is always equal to the PDF of the source random variable times d source by d target. If you keep this formula in mind, which we have derived logically through the definitions of probability distributions, so if you keep this formula in mind, you can easily perform these transformations on different random variables. I'll also give you another homework, the last from this topic, and that is if you have x as a source random variable, and that is a uniform random variable between 0 and 1, and you have y as a target random variable, and you have that f sub y of y is equal to lambda e raised to power minus lambda y for lambda greater than 0. You derive y as a function of the source random variable x. So the distribution of y is given, which is the distribution of the target random variable in this shape. X is source random variable, but its distribution is already given. It is uniformly distributed between 0 and 1, and you need to find the relation between x and y, or in other words, you have to write y in terms of x. This is simple, but it needs a little brainstorming. So please do perform this uh, this example. Do try to solve this example. So last but not the least, I'll quickly give you what we mean by conditioning a continuous random variable. It is last quick topic of this chapter. Conditioning a continuous random variable. This should be easy. This is already known to you that the PMF, conditional PMF, can be obtained by dividing the original PMF by the probability of the conditioning event. So if here, in case of continuous random variables, we'll write it as f sub x given b of x, and this is nothing but the PDF of the original random variable divided by the probability of the conditioning event, and obviously all x should be within b, and it is equal to 0 otherwise. I'll do a quick example which will clarify the concept, but remember, this is how we find the conditional PDF of a random variable given b has occurred. I'll solve an example for this topic and then we'll end the lecture. So the example is simple. Suppose t is the duration in minutes of a phone call in a certain exchange, and the distribution of this phone call or call time is given as 1 by 3 e raised to power minus t by 3 for t greater than or equal to 0, and it is equal to 0 otherwise. For calls that last at least 2 minutes, what is the conditional PDF of the call time? So you see, this is an exponential distribution with parameter 1 by 3. Your conditioning event is t greater than 2 minutes. So first you will find the probability that t is greater than 2 minutes. So you will put t greater than 2, or and then you integrate this distribution, which means you will integrate from 2 to infinity this expression, and you will get some value, and then you will utilize this expression, which means you will divide this original PDF by the probability that t is greater than 2, and ultimately you will be able to find the conditional expected value for all the conditional PDF for all the calls that last at least 2 minutes. So this was a quick look at what we mean by a quick revision of what we mean by conditioning a continuous random variables. Dear students, I'll end this chapter here, and we have been able to discuss many topics in this particular chapter. The last most important topic was how to transform a continuous random variable into another continuous random variable. We did two examples in that on that topic, and I gave you one interesting homework. Please do attempt this homework, and this will strengthen your understanding about the topic. Thank you very much for your time.